some fun together looking at perpendicular bisectors and seeing that we can actually use theorems about perpendicular bisectors inside triangles to reveal all sorts of interesting things about various lengths. Let's check it out together. So here we're given this particular triangle, and we're told that segment KZ, line segment LZ, and line segment MZ are the perpendicular bisectors of triangle GHJ. Now, we're supposed to use the given information to find the length of each of the segments here. Now, if you look at this, by the way, this figure is not quite drawn to scale, but that's okay. It doesn't matter. All we care about is what we are told to be true. And so, in fact, we're told these are perpendicular bisectors, which means, I'm going to label this right in here, that we have right angles here. So that's a perpendicular bisector. This length is the same as this length. This length is the same as this length. And this length is the same as this length. So that's what we know. And we also know that the perpendicular bisectors will always meet at a point. That's Z. And we also proved for ourselves that, in fact, that Z has a really cool property, which means that it's equidistant from the vertices, which means if I put in here 1, 2, 3, 4 marks, then this is 1, 2, 3, 4 marks, and this is 1, 2, 3, 4 marks. So that's everything we know. Now let's see what else we know for this particular question. Well, for this particular question, we know that ZM equals 8. So ZM, that's this thing right here, equals 8. I'll write that in. It has a length of 8. ZJ, that's this thing right down here, is equal to 30. So that's this thing right here. And then LJ, now where is L? LJ is right here. That actually equals 24. I'm going to mark this to be clear on this. This right here is 24. Okay, now, what are we supposed to find? Well, we're asked to find, first of all, ZG. So where is ZG? It's like a kind of a where's whatever that character is. ZG, there it is, right there. Well, look, we know that since that's going from this point of intersection of all the three perpendicular bisectors to a vertex, they all have the same distance to any other vertex, and I see this one is already given to be 30. So in fact, I immediately know this is 30. So this equals 30. That was easy. Boop, done. Now, what about HJ? Where's that? HJ is this entire side. Well, look, we know this is 24, and you can see by the marking this is also 24. Again, not necessarily drawn to scale. And so therefore, what's the whole thing? It's 24 plus 24, which is 48, and so this equals 48. So there's the first answer, there's the second answer, and we're good to go. Cool. So let's take a look at another one together where we can actually take the same exact triangle, same exact information, but now given some different given stuff. So again, just to recap, these are perpendicular bisectors. So we see they're perpendicular, but they also bisect. So I'm going to call this 1, 1, this 2, 2, this 3, 3. And again, we know that the distance from that point of intersection out to the vertices are all equal. So I'm going to call them 4 marks. That's everything we know plus the right angles. Now, let's see what else we know. Now we're also told that ZG in this triangle, where is Z? ZG, this thing right here is 80. So we're told this is 80, that length. LZ, where's LZ? Oh, LZ is right here. That thing right there is 15. And GJ, where is GJ? GJ is right here. GJ, this whole thing right here, is 126. So, what are we supposed to find? We're first supposed to find ZH. Now, where in the world is ZH? That's this thing right here. Well, look, we already know that that has the same length as this, because, in fact, the distance of the point of intersection of all the perpendicular bisectors of a triangle, of course, that point of intersection is equidistant from the vertices, and since this is 80, we know this is 80, so that's pretty straightforward. That's just 80. That's pretty easy. And what about MJ? I actually had a friend named MJ once. MJ is right here. Well, look, it's this length right here, which we see is equal to this length right here, and those two things together equals 126, so this is going to be half of 126, and so, in fact, this is going to be 63. And so we see the first one has length 80, the second segment has length 63, and we've done it. Interesting to see that just knowing theorems about perpendicular bisectors and how they relate inside of a triangle allows us to actually find the lengths of particular line segments just given a few pieces of information. As always, we get a few puzzle pieces and our minds build the entire puzzle. Have fun building the puzzles in your life, and I'll see you soon. You know, if we are given the coordinates of the vertices of a triangle, we can actually compute the circumcenter. Let's actually see how to do that. So, we want to graph the triangle with these given vertices and then find the circumcenter of that triangle. So, where do we start? Well, let's just first of all graph the triangle real fast. So you can see A is located at negative 5, 3, so up here. That's A. B is negative 1, 3, so that's up here. And then C is negative 5, way down here. And so that's B, by the way, and this is C. I'm drawing kind of a quick little picture. If I were you, I'd be using straight edges and so forth. And so if you actually were to do that, like if you were actually to take all that whole thing and use straight edge and so forth, it would look like this. Look at that. Beautiful. Now, so there is the triangle, so we graphed it. Now we want to find the circumcenter. So you know what that means? That requires us to find the perpendicular bisectors. We know they're going to intersect, and that point of intersection is it. Now here's the sneaky thing. Since we already know that the three perpendicular bisectors will intersect at a point, we don't have to find all three perpendicular bisectors. All we need are two lines that intersect, and that intersection will be the point of intersection that all three of them must actually share. So in fact, we could actually be a little lazy here, which is always good. Lazy is smart. And look at this, and here's what I notice. I notice that, in fact, it's going to be easy to find the perpendicular bisector of this side, and it's going to be easy to find the perpendicular bisector of this side. The perpendicular bisector of this side is going to be a little more work, but I can avoid that entire bunch of work by simply finding the perpendicular bisector of this, drawing that line, drawing the line that's perpendicular bisector of this, and seeing where they intersect, and they must intersect at the point of intersection of all three. So knowing that all three are going to intersect means we only need to find two of them. So first of all, what's the perpendicular bisector here from this side, AB? Well, you can see it for yourself. If this point here, one way to think about it is find the average between negative 1 and negative 5. Or you could just literally eyeball it and see that I've got 1, 2, 3, 4, so that I go 2 over, which is right here at negative 3. Or you could take negative 1 and subtract, you could take negative 1 and add it to negative 5 and divide by 2, and you get negative 3. Either way, what we see here is that x equals negative 3 is in fact the line that represents the perpendicular bisector to AB. So I could actually graph that. I'll graph it in green. Settle down, settle down. There we go. So you can see that it's perpendicular because AB is definitely horizontal. You can see it on the grid. And you can also see it because AB has the same y coordinates. And this is vertical. And so it's perpendicular, and you can see it's right in between. 2 units over, 2 units over, and so forth. Now, what about here? How about AC? Now, AC you can see is vertical, and you can see that because they share the same x values, so we're absolutely certain that it's vertical. So all we have to do is take a look at the point that's in between A and C. You can count down 1, 2, 3, 4, 5, 6, 7, 8. So we're going to go 4 down. 1, 2, 3, 4. So it's going to be here at negative 1. Or you could actually just add these numbers. So take negative 5 and add 3 and get negative 2 and divide by 2 and you get negative 1. Either way, we see that y, it's a y value, right here, negative 1, and that is
I'm good. Yeah.
The perpendicular bisector
Cookie break?
Yeah.
of each. And so, where do they intersect? Well, of course, they intersect, you just read it off here. X equals negative 3 and y equals negative 1. And what does that look like? Well, that looks like this dot right here. This dot right here, which maybe I can actually make even more visible. this. And so the coordinates of that point right there are x equals -3 and y equals -1. And that is the circumcenter. Now the real cool thing here is that we never actually had to find the perpendicular bisector of CB, which you can see is some kind of skewed line, and so it'd be harder to find the perpendicular bisector. But now we know exactly where it would be located. It would be located here and then go up in a perpendicular way. So we actually know what it would look like. Interesting little piece of trivia here. Notice that the circumcenter is not inside the triangle like so many of the other examples that we looked at. Very peculiar, and yet that theorem that we know about the circumcenter still holds. Namely, the distance from that point to the vertices, in fact, will always be equal. And check it out. This point to here, that distance, this point to here, that distance, well, those are definitely equal because, in fact, we know that this is going to be the bisector, right? The bisector is going to pass right through that. And if you take a look, and even visually you could see it, the distance from A to this point right here is the same as the distance from this point to B. You can see it just by the symmetry of the picture. So this distance is equal to this distance is equal to this distance. So that theorem still holds. But notice that we never ever said that the circumcenter has to be inside the triangle. Here's an example where it's right on the edge. And we found the coordinates. So if you're given the coordinates of the vertices of a triangle, you can do all sorts of stuff, including finding the circumcenter. Have fun looking at the circumcenters in your life, and I'll see you soon.